A modern house in extreme summer heat. Air shimmering outside. AC units running at full load. A central air conditioner shuts off during a blackout. Silence replaces the sound of compressors. A house without electricity becomes a sealed heat trap. Inside minutes, modern comfort disappears when the grid fails. But beneath the same house, something else keeps working. A buried system made from clay pipes continues moving cool air without electricity, without refrigerant, and without moving parts. Slow reveal of terracotta pipes buried underground, airflow diagram overlay. This system is built for almost nothing in cost, yet it survives where modern systems collapse. To understand it, we need to start with how modern cooling fails. Massive heatwave over a modern city, power grid strain visuals. Modern air conditioning depends on a fragile chain of electricity and mechanical compression. A central AC unit works by compressing chemical refrigerant gases. That process requires continuous high-voltage electricity. When heatwaves hit places like Texas, Arizona, or California, millions of systems switch on at the same time, power plants and transmission lines under heavy load, heat distortion. The electrical grid reaches critical demand. Power plants struggle to keep up. Transmission lines heat up and physically sag. Transformers overheat under pressure, grid operators in control room initiating load shedding. To prevent total collapse, operators begin rolling blackouts. The system sacrifices comfort to save infrastructure, dark suburban neighborhood during blackout. The moment power stops, modern homes change function. They stop being shelters. They become sealed heat traps, interior of modern insulated home heating up. Modern homes are designed for efficiency. Plastic vapor barriers. Sealed insulation layers. Double pane windows. But when cooling stops, that insulation becomes a problem. Heat cannot escape. Body heat builds up. Within hours, indoor temperature can exceed outdoor temperature. Ancient desert architecture in Persia and Mediterranean regions. Long before electricity, humans survived extreme heat in harsh environments. Ancient Persia and Mediterranean civilizations faced similar temperatures without mechanical cooling, ancient wind towers and underground cooling channels. They did not use machines. They used the earth itself. They developed systems that moved hot air underground, cooled it, and brought it indoors. Cross-section of Earth cooling system concept. Today this concept is known as an earth tube system. It is based on one simple principle. The ground stays cool even when air above is extremely hot. Underground soil temperature diagram. At surface level, heat can reach extreme temperatures. But only the top layer of soil is affected. Below 4 to 6 feet, the earth becomes stable. Thermal gradient illustration showing surface versus deep soil. At that depth, soil maintains a steady temperature of roughly 50 to 60 degrees Fahrenheit depending on location. This remains stable all year, heat sinking into ground mass animation. The earth acts as a massive thermal sink. It absorbs heat continuously without overheating. Ancient Persian airflow cooling underground. Ancient engineers used this naturally stable temperature to cool air. Hot air was pulled underground, cooled, and redirected indoors. Modern earth tube comparison, PVC versus terracotta pipes. Modern DIY systems often use PVC pipes. But PVC is an insulator. It slows heat transfer. That reduces cooling efficiency. Close-up of terracotta pipe texture, porous surface. Terracotta behaves differently. It is porous and thermally conductive. It allows heat transfer from air into surrounding soil, hot air entering terracotta pipe, heat bleeding into soil. When hot air enters the pipe, heat moves through clay walls into the cooler earth. The surrounding soil absorbs the energy, moisture interaction inside clay pipe. If the soil is damp, evaporative cooling can also occur. Moisture absorbs heat as it evaporates, reducing air temperature further. Backyard trench excavation. Building this system depends on simple geometry and labor. The system is not complex mechanically. It is a layout problem, deep trench being dug 4 to 6 feet. Step 1, dig a trench. Minimum depth is 4 feet. 6 feet works better if conditions allow, long pipe layout, 50 to 70 feet. Length matters. Air needs time to transfer heat. Short pipes do not cool effectively, terracotta pipes connected end to end. Unglazed terracotta drainage pipes are placed along the trench. Diameter typically 4 to 6 inches, mesh cover on intake pipe. The intake must be covered with mesh. Without it, insects and animals can enter the system. Pipe slope diagram 1 to 2%. A critical rule, slope. The pipe must have a 1% to 2% downward slope away from the house. This controls water movement inside the system, solar chimney airflow pulling air. Air can be pulled passively using a solar chimney. Warm air rises and exits, creating suction, solar panel powering small DC fan. Or a small DC fan powered by a solar panel can move air actively. The system becomes self-powered, thermometer comparison, outdoor versus cooled air. This system is not a freezer. It is a pre-cooling system. It reduces extreme heat to more comfortable levels, air cooling from 105 degrees Fahrenheit to 75 degrees F. Hot air can be reduced significantly. But it cannot match industrial air conditioning output, condensation forming inside pipe. A major issue is condensation. Hot air contains moisture. When cooled underground, water vapor condenses, water droplets collecting in pipe bottom. If pipes are flat, water accumulates. This leads to stagnation, mold and bacteria growth inside stagnant pipe. Without proper slope, mold and bacteria can form. Air quality becomes dangerous, proper drainage to gravel sump pit. The slope ensures water drains away from the house. It exits into a gravel sump pit, climate comparison map, dry versus humid regions. Dry climates like Nevada, Arizona, Texas perform well. Humid regions require careful design. Moisture control becomes critical, modern home with hybrid cooling system. Traditional AC is a rented system. It depends on payments, maintenance, and grid stability, grid failure scenario again. When the grid fails, comfort disappears instantly. This system behaves differently, earth tube infrastructure integrated into house. Earth tube systems are infrastructure, not appliances. They do not rely on fuel or electricity, solar panel plus fan plus underground pipe synergy. They combine solar energy, airflow, and geothermal stability. No refrigerants. No compressors. No fragile electronics, earth cross-section showing heat absorption. Heat is transferred into the planet itself. The ground absorbs it continuously, split screen, AC system versus earth tube system. Modern AC is powerful but fragile. Earth tube systems are simple but limited, hands digging soil, installing pipes. One depends on industry. The other depends on geology and gravity, sun powering solar fan. The sun powers airflow indirectly. The earth stabilizes temperature, underground pipe glowing with airflow visualization. This system uses no refrigerant. No compressor. No electricity grid dependency, house remaining cool during blackout. Even during power failure, airflow continues, quiet home with passive airflow. This system does not replace modern air conditioning completely. But it changes what happens when everything else fails. It turns the ground beneath your feet into a cooling resource. The question is not whether modern AC is better. The question is how dependent you want to be on a fragile system. If you enjoyed this documentary, be sure to like, subscribe, and let us know what topic you'd like us to investigate next. And if you're interested in more forgotten technologies and hidden engineering solutions, check out the next video on your screen.